Interconnect routing techniques. Up till we discussed about the flow of system on a chip. Now we will study the chip level layout and the circuit design. The basic objective of this design are area, delay, and the power flow planning is called as chip level layout design. The floor planning is divided in a three phases. First one is block placement. First one is block placement. Second one is global routing and global routing. And third one is detailed routing. In addition to this, the layout design is divided into these are the three phases, four planning phases, except that the layout design are divided into two types. First one is placement. Second one is routing. The global routing is mainly used for assigning the wire to routing channels between the blocks, whereas the detailed routing designs the layout for the wiring. Global and detailed routing design layouts for the signals use methods to route power further in order to minimize the clock skew and clock are distributed through the integrated circuit. Let's see one by one. We will see first global routing. Let's see first global routing. In the global routing, the first probe line is perpendicular to the face and hold the pin to first obstacle found out in the chip. If other pin is reached from this probe line, then the far end of the probe line and perpendicular line is needed. A probe line stops switch box edge. The such stops when the probe line is runs past the route between the pin follow the probe lines. In order to select the global routing, the best detailed routing for all the channels and switch box is selected. However, estimating the exact result using the detailed routing is a challenging task. Although the density gives good utilization without routing the channels, and the main goal here is to assign the wire to the rules used in a routings are first net to route should have critical delay, then route the wire early to get them out of the way. Don't free freed to try rip up the reroute wires. Next, see what is switchbox routing. Switchbox routing, I will show with a figure. Here, this is the figure of switchbox routing. Switchbox routing is mainly used to make place for the more wires. And the next figure which is shows the switchbox mainly applicable to the route the wire and track assignment at the end indicated the point of the switchbox. This is the blocking example. In switchbox, fixed pin are used to suggest layer assignment and it is apply the same layer to the root, both horizontal and vertical assignments. Next topic we will see wiring parasitics. In CMOS process, several metal layers are used in interconnect wiring. Although 3 or 4 interconnect layers were sufficient for the network with a million or so FETs, the high density compact systems are designed. On-chip wiring is important to the circuit designer to make a chip operational. Consider a wire shown in a figure, this figure, shown in this figure, which has the width, W, distance D, and the material layer with a height H and parasitic elements include the resistance and the capacitance. This is the geometrical structure of the wire. Let's see wire resistance. Wire resistance. The resistance of the wire is given by the equation R here. The resistance of the wire is given by the equation R wire that's equal to PD by WH. Here WH is the area height into width, and this is rho D, where the rho is the resistivity in the unit of ohm per second, ohm centimeter, and A is WH is the cross-section area of the line. Although this expression can be used directly, a more useful formulation for the use in chip design is based on the use of sheet resistance RS, which is given by R sheet that's equal to rho by H. The sheet resistance is useful as it can be directly measured on the test structure in the laboratory. Once the R sheet is known, then the total resistance of the line that has the width W and spans a distance D given by R wire equal to R sheet into N, where N is a D by W, is the number of square of the dimension W into W encountered by the current. This can be seen by the top view of the interconnect wire shown in this figure. Therefore, RS is having unit of ohms per square in the process as the minimum line width has decreased, the thickness of the material layer is large. Most of the interconnect are thicker than they are wide. So these are all about wire resistance. Let's see about the wire capacitors. Capacitor is nothing but the interconnect capacitance is the limiting factor in a high-speed circuit. Here shown in this figure, this is the figure of the wire capacitor. The capacitance equations used here having the unit capacitance per unit length, that is Faradays per centimeter. The total wire capacitance is given by W C wire that equal to C into D. The expression for the C is given by C is equal to epsilon. Here, this is the equation for the C. C equal to epsilon naught x W by x OX. The unit of C is above equation is a F by centimeter. However, since this formula ignores the fringing electric field at the edges, the modified equation of the C is given by C equal to epsilon OX, that's in a square bracket 1.15 into W by X OX plus 2.8 into H by XOX raised to the power of 0.222 farad per centimeter. Therefore, the value of capacitance is higher by the including the fringing field shown in this figure. The second figure, here we can see the fringing fields. So this is all about the wire capacitance. Let's see RC wire model. This is the RC wire model. So here figure shows the representation of the long wire in terms of distributed RC section. The signal propagation in the wire, which includes the distributed resistance and the capacitance of the wire, the impedance of the driving source and the load impedance due to high resistance, very long wire, the transmission line affects larger. The wire is expressed by the several RC sections here shown in a figure. And further, when the sections are increased, it is expressed as this equation. This is the equation where x is equal to distance from the input, r is a resistance per unit length, and c is a capacitance per unit length. The solution of this differential form from yield an approximate signal delay of can be expressed by this equation. And here R is a resistance per unit length and C is a capacitance per unit length and L is the length of the wire. Here L square shows the delay is a larger by RC effect for the very long wire. In M order to improve the speed, the line is segmented into various sections and buffers are inserted in a section. So this is the figure where segment segmentation of polysilicon line. Here, RS is the output resistance, is receiver input capacitance, RT, CT are the total lumped resistance and capacitance of the wire. This is the sample model of the RC delay calculation. The wire parasitic role in a routing. In this case, the transitions from the routing layer can be provided an extra resistance to the wire. This kind of resistance is popularly known as contact resistance. Therefore, the signal layer wire routing technique is used to avoid the unnecessary extra contacts further to reduce the contact resistance and the contact hole diameter in the increased, which leads to crowding effects. Next is design validation. Design validation. Design validation. The design validation shows the structure and performance of the subsystems. In this, the floor plan is checked and chip after assembly is checked. Now let's discuss about off-chip connection. Off-chip connections. The packaging is the major challenge to the IC designer. In packaging, the pads are need to be connected to the IC internals and the surrounding blocks. In this case, IC engineer is responsible for designing all the assembly of the pad bonding. Therefore, here we will review the packages and the problem involved in the packaging. The necessary things involved in the packaging are the package pin should have manageable solder connections, and the package provides the material mechanical support to the chip, and the packages should conduct the heat away from the IC to the surroundings. I will show the figure of the general packaging or generic package here. Here, the design or generic package for IC. The packages also has the electrical problems which are caused by the inductance of the pins and the printed circuit board attached to them on chip wire. Further package inductance introduce significant voltage fluctuation. Then IO architecture and pad design. Pads are normally distributed around the edge of the IC, and the pad should be large enough to have input and output circuits, right? Here the figure shows the architecture of the pad, which is having a pad frame. Here the pad is built to a standard width and height. The pad has large VDD and ground lines also, and the pad includes large piece of the metal. If the pad requires external circuitry, it is usually put the side of the pad closest to the IC core. The IC core is a middle of the pad ring. The placement of the pad around the ring is found in order of pins the package. The wire to the package should not be crossed without the shorting. Therefore, if the package pins are required in order, the pad must be arranged in the same order. VDT and ground pads are simple to design because they require no circuitry, and this kind of pad is bigger than the single wire. Therefore, in this case, the current is limited by the wire. This is all about the architecture and pad design. Let's discuss about signal integrity issues. I will write the headline here. In a recent day, signal integrity is a critical issue to the VLSI designers. The signal integrity problems are related to electromagnetic and are in terms of EMI and EMC. In the digital system applications, the signal is transmitted from one component to other in the form of logic, high or low. At the input of the receiver, the voltage above the reference value is taken as the logic high, whereas the voltage below the reference value is taken as the logic low. Then furthermore, also depend on the waveform signal, waveform distortion or having the various mechanism and the noise problem that are the reflection noise and crosstalk noise and power ground noise. The rise time and signal integrity due to significant improvement of the chip fabrication technology. The silicon size is shrinking and transistors channel length is reduced into submicron range, hence the speed of the logic circuit increases. In a depth, submicron technology is related with dV by dt and di by dt, ranging the and the crosstalk power ground switching noise are also existing. Since the system with a faster clock frequency has the lower rise time and signal integrity challenges are increasing. What about the crosstalk noise is nothing but the chip packages. In the chip packages, a pair of the parallel conducting wire separated by the uniform distance and the wire is socket are used. A pair of the metal plane with an attached wire, another type of the transmission line is used. The transmission line are used for transmitting data from point A to point B and the transmission line parameter R per unit length R, L, G, C. For the transmission line structure, the parameters are found by the numerical techniques. The electromagnetic coupling between the various transmission lines lead to crosstalk, hence the noise pickup and adjacent signal lines used to negative logic switching. When the active and multiple lines are switching, crosstalk also involves timing depending upon the switching directions, and the delay significantly increases and decreases. Because of the spacing between the lines and the crosstalk related to the signal rise time challenges, in order to limit the crosstalk, the line space has to be increased and Ground guarding band is to be added. Let's see EMI immune design. This is the last topic of this unit. Let's discuss about EMI immune design. EMI design consideration. The following. Here, these are the following actions discuss design technique that are applied to minimize the EMI emissions. Some ideas have been incorporated into the designs and some must be implemented by motherboard designers. Let's see one by one. First one is spread spectrum clocking. This one. Spread spectrum clocking. In a spread spectrum clocking, the processor clock frequency is changed. Here, this figure shows. Here, this figure shows spread spectrum modulation spectrum with a decreases radiated emission over the wider frequency band. Therefore, instead of maintaining a constant system frequency, spread spectrum clocking modulate the clock frequency and shows the reduction in a peak radiation level to reduce the EMI. So second one is differential clocking. The differential clocking need the clock oscillator to apply clock and clock bar traces to optimize the use of the differential clocking. Clock lines are routed parallel and the reduction in EMI mainly due to differential clocking is because of H field cancellation. Here the figure of cancellation of H field through the inverse current. Your figure shows in this figure lower H field which leads to reduction in a EMI radiation, and differential clocking also reduces the amount of noise coupled to other traces. These are all about the EMI immune design. And another small topic is there, that is a floor planning. This is the floor planning. A floor planning is the important step of the VLSI chip design. In this step, the various logic blocks are placed in a chip for the and after placement ODF and the logical blocks. The routing area of the blocks is also determined in the step. These steps determines the size of the die and creates the wire tracks for the placement of the standard cells. The floor planning also creates the power ground connections and the constraints of the floor planning setup steps are minimize chip area, make routing eyes, and reduce signal delay. Now, a day floor planning is more important in a physical design, and the main step in the physical design flow are design netlist, floor planning, partitioning, placement, and clock tree synthesizers, routing and physical verification, and GDS second generation. So this is all about the floor planning. The unit second is over here. We will start unit 3, the next lecture. This is enough for the day. Thank you.